Hey everyone, welcome back to Daily Dose of Space. Today, we've got a pretty fascinating set of updates, starting with a major new discovery about the early solar system that might literally rewrite the textbook model we've used for decades. Then, we'll revisit the interstellar visitor 3I, ATLAS, including a new breakdown of what scientists think is happening as it approaches the Sun, and why the fragmentation we're seeing actually lines up with current interstellar comet models. And finally, we'll touch on two quick updates, one on the DART impact crater analysis and one on a new method for detecting exomoons. Let's jump straight in. A new model of the early solar system. For decades, astronomers have relied on the NICE model and the Grand TAC model to explain the early solar system, basically the big picture idea that Jupiter and Saturn migrated inward and then outward, reshaping everything around them. But a new simulation published this week suggests something surprising. The Sun's magnetic field may have played a far bigger role than we thought, and not just in pushing dust around, but in actually defining which planets grew where. Scientists at the National Astronomical Observatory of Japan used a high-resolution magnetohydrodynamic disk model, basically a realistic simulation of gas plus dust plus magnetic forces, and discovered the young Sun generated strong magnetic winds. These winds created pressure bumps in the protoplanetary disk. These bumps acted like cosmic traffic jams, trapping solid material. These trapped rings became ideal sites for rapid planet formation. This explains a few long-standing mysteries. Why the inner solar system has small rocky planets. Why gas giants form farther out. Why the asteroid belt contains both carbon-rich and dry material. Why Mars is so small compared to Earth. The model essentially suggests the Sun was sculpting the disk from the inside out, creating the zones where planets could form. This new model actually lines up better with observations from the ALMA telescope, which has photographed young star systems with perfect ring-like planet-forming structures. For years, we thought those rings were caused by forming planets carving gaps. But now it might be the opposite. Rings may form before planets and allow planets to form inside them. This could fundamentally change how we look for habitable worlds around other stars. Updated. Look at 3I ATLAS. You've probably noticed that 3I ATLAS has been showing up everywhere in space news lately. And for good reason. It's only the third confirmed interstellar object we've ever detected, and its behavior is already teaching us new things. Let's break down what we know. In the last couple of weeks, multiple observatories have confirmed that the object is losing cohesion, shedding pieces, brightening irregularly, and showing asymmetrical dust emissions. This is totally expected. Interstellar comets spend thousands or millions of years exposed to cosmic rays, become structurally weak, often consist of brittle, loosely bound material, heat up rapidly when entering a new star system. Fragmentation is not a sign of artificial origin. It's a sign of extreme age and extreme temperature contrast. A few things stand out. Its orbit is deeply hyperbolic, a clear sign it's not bound to the Sun. Its composition appears more carbon-rich than 2I Borisov. Its brightness curve suggests a higher volatile content. Its fragmentation pattern matches long-period comet breakups, but with some interstellar quirks. One particularly interesting observation: the dust it's releasing seems unusually fine and reflective. This may indicate exposure to low-density environments for tens of thousands of years, possibly the interstellar medium itself. Every fragment, every dust cloud, every outburst gives us a rare sample of material formed around another star. This is literally the first time in human history we've had a stellar system sample delivered naturally passing through our front yard and observable from multiple telescopes simultaneously. We're basically looking at a piece of someone else's solar system. Quick updates from the last 48 hours. A new study shows the crater on Dimorphos is wider than expected, shallower than expected, and surrounded by much more redistributed material. This suggests the moonlet was structurally weaker and more porous, meaning the momentum transfer from DART was far more efficient than predicted. This is great news for future asteroid deflection strategies. Researchers at MIT have proposed a new technique that uses transit timing noise, tiny irregularities in the timing of a planet crossing its star, to identify potential exomoons even when the moon itself is too small to see. If this works, we could suddenly go from 2 tentative exomoon candidates to dozens. And that wraps up today's Daily Dose of Space. If you enjoyed the breakdown, consider liking the video to help it reach more people. And as always, if a major discovery drops, you'll hear about it here first. Thanks for watching, and I'll see you tomorrow.